All right, so it is 11. I'm going to distribute the roll sheet in the hopes that more than, let's see, there's 5 of you and 3 people online, including me. So that's 7 out of 18 people are showing up for today. So that's terrifyingly low. I sure hope this stuff doesn't show up on a test. Oh, wait, it's going to.
No, it's cold today. A lot of people test.
Yeah, it's his birthday. He's turning 20, maybe. 21. 21. Oh, so he's not hammered right now. He's showing up to class being a responsible young adult. Whereas these other guys are playing fast and loose with their grade. All right. Okay, so today we are going to be talking about filters. Because that's what you guys said that you wanted to talk about. Or were willing to listen to me talk about would probably be a better. All right. So introduction to filter circuits. So let's first talk about what a filter is. Is an electrical circuit that is used to accept or pass certain frequencies and reject or stop all other frequencies. There are four different general types of filter classifications. And so we'll talk about what those are right now. So our first filter has a response that's going to look something like this. So what we're doing is we are measuring the amplitude. I'm going to call that the magnitude of H. We'll talk about what H is in a moment, versus frequency, where frequency is, here we're going to have it listed as an angular frequency. So it's going to be as a function of omega. So our first type of filter that we are going to talk about is what is called a low pass filter. What I have drawn here is what is called an ideal low pass filter. Also, it's commonly referred to as a brick wall filter, okay? And so what this filter does, there is a specific frequency right here. We're going to call this omega C. And it is what's known as the corner frequency or the cutoff frequency. And so what this filter does is that every signal operating below that frequency omega C gets passed. So we call everything below omega C the pass band. And then everything above omega C is completely attenuated or filtered out. And so we're going to call that the stop band. Now, an ideal low-pass filter can never be realized, physically realized. It's literally impossible to do. So what we should expect really is a response that looks a little bit more like this. Except that I can't draw for crap today. Let's try this again. And this point right here, more specifically, let me draw a line right here, is 3 decibels lower than the maximum amplitude. So our corner frequency occurs at 3 dB lower than our maximum amplitude, where a decibel, so our magnitude in decibels, H measured in dB, is equal to 20 log V out over Vn. So our transfer function is a measure of the voltage gain of the system. It just depends on frequency, okay? So this is what our low pass filter does. We are going to be looking at first order and second order low pass filters, which means that they have 1 or 2 energy storage elements. There are absolutely higher order low pass filters. And what we should observe is that for every order you get, this gets steeper and steeper and steeper. So that roll off better approximates the ideal low pass filter. All right. The next one that we are going to be talking about is what is called a high pass filter. So here's omega. Here's the magnitude of our transfer function in decibels. We have a corner frequency again, omega c. All right. And so in a high pass filter, everything below the cutoff frequency is the stop band. Everything above the cutoff frequency is the pass band. And practically, again, we can never create something like this. So instead, it's going to look something like this. Where this is, again, our and it's the order of the filter, meaning we add more energy storage elements. We will see that that fall off is steeper and steeper and steeper as well. Okay, so these are our 2 basic ones, a low pass filter and a high pass filter, and we can effectively combine these 2 types of filters to make 2 other filters. So these guys can be recognized as first order filters. These next guys cannot be, since they're a combination. What's up? That is the difference between, so it's 3 decibels in magnitude lower than its maximum value, okay? Where a decibel is a measure of the gain. So instead of saying immediately when it falls below, we say it's 3 decibels is when it falls below its maximum value, is when what we consider to be the cutoff frequency. The 3 decibel frequency, and we'll get into this maybe in a little bit, is also known as the half power frequency. And so what that means is that if we have a load connected to this guy, when we're at frequencies less than our cutoff frequency for a high pass filter, less than half of the power is actually delivered to the load. When we're at frequencies above the cutoff frequency, over half of the incident power is actually delivered to the load. So this is a pretty good metric of whether or not your whatever you have your filter connected to is actually receiving energy. What's that?
Like, what would a normal maximum
So it really depends. So 6 decibels would mean that your output is roughly, let me double check this here. I think it's 4 times or thereabout. Nope. 20 log 2.20 log, not natural log. Yeah. Okay. So if you had an amplitude of 2 decibels, that would mean that roughly your output signal is about 6 times larger than your input signal. So the decibel gain of a system can easily be tens to hundreds of decibels, depending on what the application is. So think about a satellite radio, okay? You have a satellite in a geosynchronous Earth orbit, some distance away from the surface of the Earth, right? You guys have had Physics 202, so you should recognize that electromagnetic waves, their energy dissipates as a function of distance away from their target, right? So if you have a satellite in space broadcasting a signal at a megawatt of power, by the time it reaches the surface of the Earth, you could be looking at only milliwatts of energy, best case scenario. So an amplifier, say your car's Sirius XM radio or whatever, has an amplifier that can take that very small, maybe millivolt or smaller signal and amplify it up in such a way that it could be used to drive a speaker and you can hear it and all that kind of stuff. So in that system, you might have a gain of 60 to 80 dB pretty easily. It all depends on how high you want your output versus how small your output is. So it's hard to say this is kind of the upper maximum and this is the lower maximum. I will say that when you're designing filter circuits and stuff like that, you're really looking for like negative 60 decibels of attenuation for saying that the signal is entirely killed. So if you're trying to electromagnetically shield something, what you're looking for is when you, like if you have a copper barrier or something like that, and you want to make sure that it's acting as a good shield, you would apply a signal to one side of the copper barrier and your antenna on the other side should be picking up that same signal, but at a 60 decibels lower for that shielding to be considered good. So it's all relative, but there are certain metrics within certain fields that are used. Okay, so our high pass, no, excuse me, not high pass filter. So the next one we're going to talk about is what's called a band pass filter. And a band pass filter has a center frequency, omega naught. And spoiler alert, this omega naught is effectively the exact same omega naught we were talking about when we did transient analysis of RLC circuits. It is the resonant frequency of the filter. And so it is the frequency at which all of the capacitive and inductive reactances cancel each other out. So everything looks purely real. All right. And then in addition to that, we have a frequency which I'm going to call omega L and a frequency which I'm going to call omega H. So low and high. Our response ideally is going to look something like this. So everything below omega L is in the stop band, and everything above omega H is in the stop band. Everything between omega H and omega L is the pass band. So this is why it's called a band pass filter, because only a certain band of frequencies gets accepted, everything else gets rejected. Omega L and omega H are both 3 dB cutoff frequencies, so we should expect behavior that looks something like this. In a non-ideal case. So both of these guys are 3 decibels below the maximum amplitude. In my other class that I'm teaching right before you guys, we were doing the frequency response of transistor amplifiers, and all transistor amplifiers behave like bandpass filters to some extent, meaning that at very low frequencies, the coupling capacitors and everything dominate, and so you don't get any good gain. In the mid-band frequencies, which is between omega low and omega high, the amplifier works very well. And at particularly high frequencies above omega H, we see that the internal capacitance of the transistor effectively turn it back into a bad amplifier again, where everything gets attenuated. So we'll use these concepts of band pass, band stop, high pass, and low pass filters literally throughout your EE career from this point on. All right, lastly, we have a band stop filter. And so in a band stop filter, we again have some resonant frequency omega naught, a lower 3 decibel frequency omega low, a higher 3 decibel frequency omega high, and what we see is a response that looks like this. So between omega low and omega high is our stop band. And then everything less than omega low gets passed. And everything higher than omega high also gets passed. And practically, this is going to look something like this, where realistically, that dip or notch in the middle might not make it all the way down to 0, or you know, it might not fully attenuate things. So just to be clear, this is a 3 dB frequency, and this is another 3 dB frequency, or half power frequency. And I should label it as a band stop or notch. Okay, so before we get into actual filter circuits, I want to talk about how and why filter circuits work, and why this is actually a reasonably appropriate place to start talking about them. So the purpose of a filter is to pass some frequencies and reject other frequencies. And you hopefully have noticed that say if you have the impedance of a capacitor at very low frequencies, it looks like an open circuit, and very high frequencies, it's going to look like a short circuit. Similarly, an inductor at very low frequencies looks like a short circuit, and at very high frequencies looks like an open circuit. So if we had a very simple circuit like this, where we have some input voltage, Vn, that varies with frequency, here's a resistor, here's a capacitor, and here is V out as a function of frequency. This simple circuit is actually a filter, okay? And the reason why it works as a filter is because at very low frequencies, we would see that C looks like an open circuit, which means V out is exactly equal to V in. And at very high frequencies, C looks like a short circuit, which means V out is equal to 0. So it passes low frequency signals and attenuates high frequency signals. So this is an example of a simple first order low pass filter. So let's dive into a more formal approach than just kind of understanding what the role of impedance and frequency plays, okay? So I'm going to define a transfer function, h of omega, as V out of omega divided by V in of omega. Since V out is a phasor, since it depends on frequency, and V in is a phasor, depends on frequency, our transfer function H, the ratio of output voltage to input voltage, is by definition a complex number. So H can be decomposed into two parts. We are going to have a magnitude of H of omega and a phase angle for H of omega. The overwhelming majority of the time, most people are only interested in the magnitude, but there are certain applications where the phase response becomes important as well. So I'm going to label these guys just real quick. So this is what we're going to call the frequency response. And this is what we're going to call the phase response. And when we simulate these guys on LT Spice and things like that, if you simulate a simple low pass filter circuit, you're going to see, or any filter circuit, you're actually going to see two lines. One, the solid line is the frequency response, and the dashed line is the phase response. So when I ask you to simulate things, it's perfectly acceptable that you're going to get two lines on your graph. You're supposed to, okay? All right, so let's look at our simple low pass filter, okay? We are going to apply some voltage V in as a function of frequency. I'm going to denote that these guys are phasors. I have some resistance R and some capacitance C. And that capacitance is going to look like an impedance of 1 over j omega C. Here is where I will measure my output V out over omega, okay? So based on this guy right here and our definition of a transfer function, how could we get the transfer function of this simple RC network? What relates the quantity V out to the quantity V in?
The quantity V out is going to be the voltage drop across the capacitor.
Sure.
So it would be voltage division.
Absolutely right. So the key to doing any of these frequency analysis of any of these filters is literally just going to be doing voltage division correctly and then algebra, okay? So we know that for this particular circuit, V out as a function of omega is going to be the voltage drop over the capacitor. So that's going to be the impedance of the capacitor, 1 over j omega c, divided by the total series impedance seen by our input signal, which is going to be R plus 1 over j omega c. And this all gets multiplied by V in of omega, giving us a transfer function, h of omega is equal to 1 over j omega c divided by R plus 1 over j omega c. So our transfer function is always just going to be the ratio of the impedances portion of our voltage division equation. So another way to think about this is we could just figure out what the output signal is if Vn has a phasor value of 1 angle 0 degrees, right? If we treat Vn as 1 angle 0 for all frequencies, then V out is exactly the same as the transfer function. So again, it's just simple voltage division. Now, I personally don't care for having fractions in my systems. And so what I'm going to do to simplify this thing is multiply by a factor of j omega c over j omega c. And so what this is going to give me is 1 divided by 1 plus j omega RC. And so this is what I would consider to be the classical definition for the transfer function of this particular filter. We already know that it's a low pass filter, but we need to do some work to prove it. Because if we try to plot this function, we would run into some issues in as much as we have a complex number, right? So we're going to need to split this guy up into its frequency response and its phase response to get a total picture of how this filter behaves. So how could I get the magnitude of this guy? So square it and square root it, close but no cigar, okay? And so what I mean by that is if you squared the complex number, you're not going to get rid of the complex number in the denominator. So you actually have to multiply it by its complex conjugate and then take the square root. But we are going to do something slightly different because we are interested in both the frequency response and the phase response. And so what I'm going to do is I'm going to express this guy as a complex number instead of having a rectangular complex number in the denominator, I'm going to have a rectangular complex number in the numerator, because that's going to let me more easily split this guy up into a magnitude and phase response. So just as a heads up, what I'm doing, recall that if we have some complex number A is equal to A plus JB, so a real part and an imaginary part, and this is the same as the magnitude of A angle theta A, the magnitude of A is simply the square root of a squared plus b squared. And the phase angle of A is the inverse tangent of B over A. So the next few steps that I'm going to be doing are making H of omega in this form, where there is a distinct real part and a distinct imaginary part in the numerator so that we can easily break things up. To accomplish that, I believe we did this maybe a week or so ago when we were looking at that circuit in the time domain and developing some relationships. So I'm going to multiply this by 1 minus j omega RC in both the numerator and the denominator. So I'm multiplying by the complex conjugate of the denominator divided by the complex conjugate of the denominator, because that is going to force my denominator to become a real number. All right. And so what this is going to give me is 1 minus j omega RC divided by 1 plus omega squared R squared C squared, or 1 plus omega RC quantity squared, however you choose to write it. Actually, I think I would prefer it that other way. So I'm going to rewrite this as omega RC quantity squared. And we could just as easily say that this one is 1 squared as well to denote what's going on there. All right, so from this, my frequency response, H of omega, is then the square root of the real part. So that's going to be 1 over 1 plus omega RC squared quantity squared plus the imaginary part, which is negative omega RC over 1 plus omega RC squared, this whole thing squared, like so. And from this, give myself enough room. I'm going to have 1 plus omega RC quantity squared divided by 1 plus omega RC squared, like so. Everybody okay with this? All right. So I can see that I have my denominator is just my numerator squared. So I can cancel this guy out to get rid of that. And what I find is that my frequency response is just 1 over the square root of 1 plus omega RC squared. All right. So we now have enough information to tell whether or not this guy is going to be a high pass filter or a low pass filter. So let me talk about how we would do that evaluation real quick, okay? So the magnitude of H evaluated when omega is equal to 0 is going to be what? 1. What is the magnitude of h when omega is equal to infinity? 0, right? Because it'll be 1 over the square root of infinity squared. So 1 over infinity is 0. So that we can see it passes high frequencies, rejects low frequencies. This must be, or excuse me, passes low frequencies, rejects high frequencies. So this must be a low pass filter. So I'm just going to put LPF. All right. So before we move on to the phase response, let's identify what our 3 decibel frequency is going to be here, okay? So the 3 decibel frequency occurs when we have half of the power, which is going to mean that our frequency response is going to be exactly equal to 1 over the square root of 2, okay? So at omega c, the amplitude of h of omega has to be equal to 1 over the square root of 2. Now, you may be wondering why we would consider 1 over square root of 2 the half power frequency instead of 1 over 2. The answer is because we're dealing only with voltages. If we were dealing with power, which is proportional to voltage squared, we would square this guy and we would see that the magnitude is exactly equal to half, okay? So our half power frequency occurs when our voltage gain is equal to 1 over the square root of 2. So that means that the square root of, so from this, we can see that the square root of 2 has to be equal to 1 plus omega RC quantity squared, which means that omega C is equal to what? So if we put, so omega RC is equal to 1, which means omega is equal to, depends on the resistor and the capacitor values, but in what way? Yeah, so 1 over RC. When you guys learn to work in the frequency domain or the Laplace transform, how many of you guys have had 245? A couple of you guys, okay. So omega C is what is called a pole frequency. So if we went up here and we looked at this representation, we can see if we, in the Laplace domain, j omega is equal to S. And so we would have 1 over 1 plus S omega, or excuse me, 1 over 1 plus S RC. This is the form, zeros are on top, poles are on bottom, and you can actually see by inspection that your pole frequency omega C is just going to be 1 over RC. So that's a very quick and easy way to figure out what your poles and what your zeros are and all that kind of stuff for your filters. But it makes no sense whatsoever until you've learned all about using the Laplace transform. So for those of you who have taken 245 before now, this is going to be really easy for you. For those of you who haven't, I'm talking about the ways to get around things and figure stuff out. All right, so our frequency response, or excuse me, not our frequency response, our phase response. Theta H of omega is by definition the arctangent of the imaginary part, which is negative omega RC divided by 1 plus omega RC quantity squared divided by our real part, which is 1 over 1 plus omega RC quantity squared. We can see that these denominators cancel each other out. And so this is going to look like negative arctangent of omega RC. And it's because the arctangent of negative something is the same as negative arctangent of positive something. So we know exactly how this particular filter behaves. We have quantified its frequency response, or how the magnitude shapes the incoming signal, and the frequency, or excuse me, the phase response, or how the phase of the incoming signal gets converted as a function of frequency. So I'm trying to decide whether or not I want to show you what this is going to look like on LT Spice or move ahead. Let's look at, I have something pulled up on LT Spice right now. This is for a particular transistor amplifier, way more complex than what we're doing in this class, obviously. But we have a low pass response, meaning what we're looking at is from effectively right here and on. So we have that roll off at a pole frequency of here about, I think it's 16 megahertz or so. And then this is how the phase behaves. If you give me just a minute, I'll throw one up that's our speed. Because you probably need to know how to set these things up. All right, so let's say we're going to do a simple RC circuit. So here's R, here is C, so somebody give me a value for R. We're going to see how good of a job our model does. Pardon? 10? All right. Give me a capacitance value. 1 farad. All right, that's easy enough. I'm going to throw in a voltage source because I need to. And I'm going to drop this guy in here. Okay, and so this is our first time we're ever going to be doing a frequency analysis on LT Spice. And so I'm going to right click on this guy and go into the advanced properties. We're not going to do anything on the left-hand side at all. We're actually just going to use this box over here that says small signal AC analysis, okay? We're able to give an AC amplitude. And so I'm going to put 1. That way, it's treating my input signal as a 1 volt signal over all frequencies of interest. So in the frequency domain, it just looks like 1 angle 0 for all frequencies. I'm going to leave my phase blank, or I can put it at 0. So I'm just saying I'm not introducing some extra phase into this, and I'm going to press OK. Let's going to label this guy right here, my output. So let's call it V out. And I'm going to edit my simulation command. And so I am going to do what's called an AC analysis. Okay. So an AC analysis says compute the small signal AC behavior of the circuit be linearized about its DC operating point. We get to choose the type of sweep. So I want to do a decade sweep. I'm going to arbitrarily say 100 points per decade. This is just going to tell us how accurate we are when we're looking at things. And let's see. I'm trying to decide what frequencies I want to look at this thing. Because we've chosen a 10 ohm resistor and a 1 farad capacitor, that means that my 3 decibel frequency should be 1 over 2 pi to make it a linear frequency times R, which is 10 times C, which is 1 farad. So I'm expecting my 3 decibel frequency at 16 millihertz. So let's start this guy at 1 microhertz and end it at 1 hertz. Just drop this guy onto here and run. Circuit doesn't have a path to ground. All right, I forgot to include ground, so let me do that real quick. Actually, that'll work. And so now, because I've chosen my input voltage to be 1, my output voltage is the exact same thing as my transfer function. And let me make this to be not green so that it's more easily visible. So the solid line is my frequency response. The dashed line is my phase response. Now, a moment ago, I said that we should expect our 3 decibel frequency to be at about 16 millihertz, right? So we look at this thing. Let me make this even more obvious. Let's see if I can do it this way. So with 3 decibel tick marks, this is my 3 decibel cutoff frequency. Right here where my finger is, this is a logarithmic graph. So if this is 10 millihertz and this is 20 millihertz, this seems like a pretty good place for 16 millihertz to be, right? So we're getting exactly what we should expect. Now, one thing that I want to point out here, just to be clear, the frequency that we are getting here is an angular frequency. The frequency that LT Spice gives us is a linear frequency. So I'm going to go ahead and say then that FC, my linear frequency, is just omega C divided by 2 pi. So that when you're making sure that things are working right with your simulations, this is the number that you should expect to see on LT Spice. All right. So we expected a low pass filter, we simulated it, we got a low pass filter response. Now, let's consider this network. You can tell me what my transfer function should be. What's up? All right, so what's it going to be? Do the simple math in your head. So it's the voltage drop over R. So that means R is going to be in the numerator, right? One over J omega C. Multiplying through by a factor of J omega C is going to give me J omega RC divided by 1 plus J omega RC. Now I'll multiply it by 1 minus J omega RC over 1 minus j omega RC, which is going to give me, let's see, omega RC quantity squared, because when I do j times negative j, that's negative 1, which is positive 1, or excuse me, the square root of negative 1 times the square root of negative 1 is negative 1, and then that is multiplied by another negative. Then I'm over here, I'm going to have, let's see, so that's that bit times that bit, plus j omega RC divided by 1 plus omega RC quantity squared. So my frequency response is going to look like this. So that's the real part squared. Then I'm going to have my imaginary part. Square that. When I combine terms, so I'm going to have omega RC quantity squared times 1 plus omega RC quantity squared in my numerator. Does everybody see that? I have omega RC squared plus omega RC squared is omega RC squared times 1 plus omega RC squared. That's what I'm trying to get at there. And then my denominator is going to look like 1 plus omega RC quantity squared, this whole thing squared. And this guy cancels out one of those powers, leaving me with a frequency response of omega RC divided by the square root of 1 plus omega RC quantity squared. So when omega is equal to 0, what is the magnitude of my frequency response? Right? Because we have 0 over the square root of 1. When omega is equal to infinity, or for very high frequencies, what's happening here? Yeah, so a 1. So we see that this guy rejects low frequencies, passes high frequencies, so this must be a high pass filter. Absolutely right. Okay. Our corner frequency, or our cutoff frequency, what do you think it's going to be? We need this to look like 1 over the square root of 2, right? So what value of omega makes that happen? 1 over RC. Yep. Nothing hard about it. So we should have the exact same cutoff frequency, which makes sense because we have the exact same components. for these simple filters, we should see that our cutoff frequency is the reciprocal of our time constant for our circuit. Probably going to wrap up a little bit early today because we could go through first order filters with inductors and we would get a low pass filter and a high pass filter with those guys, depending on where the inductors are. But the derivation is effectively almost the exact same thing. You'll get almost the exact same frequency response. You'll get the same corner frequency, but instead of it being 1 over RC, which is 1 over the time constant of an RC circuit, it'll be 1 over L over R, which is equal to R over L, 1 over the time constant of an RL circuit. So, all right. And so our last thing here to look at then is our phase. So that is going to be the inverse tangent of the imaginary portion, which is omega RC divided by 1 plus omega RC squared divided by the real, which is omega RC squared divided by 1 plus omega RC squared gives us the inverse tangent of 1 over omega RC. So now we have our magnitude response and our phase response. And so our first order high pass filter is covered. So like I said previously, there are 2 other low pass filters. We are not going to derive everything for them because it's fairly trivial. But we have this guy. Here's R, here's L. Here's, sorry, that should be BN. Here's V out. So based entirely on what we understand of how the magnitude of an inductor works, what type of filter is this? It's a high pass filter, right? Because at very low frequencies, this guy goes to 0. And so all of our signal is attenuated. At very high frequencies, this looks like an open circuit and all of our signal is passed. So this is a high pass filter. With a corner frequency, omega C is equal to R over L. And then by extension, should be pretty easy to figure out. This guy is a low pass filter with a corner frequency of omega C is equal to R over L. And I'm going to give you guys a homework problem making you derive the phase response and the magnitude response. But should be very, very straightforward. Okay, so that's enough out of me for today. So that is first order filters. So if today's Wednesday, Friday, we're going to talk about second order filters. Specifically, we're going to look at band pass and band stop filters and how they are realized. You can absolutely make high pass and low pass filters with resistors, inductors, and capacitors. And the derivation is fairly similar. So anyway, that's enough out of me. I hope you guys have a good rest of your day, and I will catch you on Friday.